Okay, I just did the screencast. I didn't record because of the sound wasn't working. Now the sound is working. I just tested it, and now we're good. So, anyway, I think where my trouble came in before was right here, and what was going on here. So first of all, we have our we've got the directionality of our electric field, P and S, and for the reasons that I stated in my in the last submission, I stand by those. I think those were right. Where I think I got confused was KR. This is R, and obviously this is not, K dot R. We've dotted them now, and R is Y, and R is y sine theta y hat plus z sine theta z hat, and then K is kx x hat plus, excuse me, kx y ky y hat plus kz z hat, and then you dot those together, and then what you get is that. So that is the direct. So R is the direction we're traveling, and which this vector is the R vector. That vector is the R vector, but it's also the K vector. So they're on top of one another, and when they're on top of each other, cosine of theta, which is you need that for the dot product, is zero. Excuse me, cosine theta of cosine of 0 is 1. So literally all we've got is we've got Kr, and but only if they were varying. R and K would we have something other than this scalar right there. So anyway, so that is that. Again, as I talked about in my previous screencast, what we've got is we've got two very different things going on. I don't know if I described it very well. This is only directionality right there. This is only involving magnitude, or actually better. This is better stated as phase. Phase shift is e to the I, and I don't know if I fully have grasped that until now, particularly as we're talking about things like Jones vectors, where you've got to use the e to the I function for the phase shift between the fast and slow vectors, or wave vectors, or waves, or whatever you want to say. But anyway, so you've got the directionality, and so while we've got our R, we solve there, and then this is our electric field, directionality. Now here's the deal, though. So again, so we've got for our in the y, so it's in the y hat direction. That would be cosine of this theta, and in the z hat direction, it's negative sine theta, and that should be right there, and that's all based on simple geometry, or simple trigonometry, and that's how we get those numbers. Now, where I also got confused is exactly what boundary conditions or pinch off meant. I thought until yesterday that meant that that z equals 0 is boundary conditions. That is not boundary conditions. That just means z equals 0. We're choosing where we're putting our interface at a very convenient location so that we can take that term out. That does not do anything about this this directional term right there. What that is due to pinch off. What pinch off does is we're saying that in this diagram here, that our electric field is we're going to literally pinch off the z hat direction, so it's infinitesimally small, so that when we calculate the electric field, the P and the S electric field, all we have to do is account for the y hat direction, because we're dealing with such a small area in the z hat direction that is virtually or that's totally negligible, virtually non-existent, so virtually 0. So by using boundary boundary conditions, we're getting rid of that. By saying z equals 0, we're getting rid of that, which leads us to that. And then this equation here then is saying that electric field on the left has to equal electric field on the right. Again, as I said yesterday. Now for the phasor diagrams, you did a screencast about that, and interestingly enough, okay, this is not what it's supposed to look like, but we've got the sum of two vectors that have has a real and an imaginary component. So we could say, hey, that's the incident, this is the reflected, and then this is the transmitted. It's the electric field that's equal to both of those. If those are not in sync like that, then these phasors would not align. So let's say that we adjust. Let's say we make our k value larger in our reflected in our incident light. What would that do? Well, let's look at the equation. Well, clearly, if we increase k by Euler's, we're going to see some increase in both the x and the y direction on the or in the real and the imaginary direction on that diagram. So if we increase k, all we would do is we would just say that gets bigger. So we're just saying that k is bigger, and obviously y is obviously we have to keep y the same for each, or we have to keep y the same for each of those. So it's not like we can make up for that with something else. So all we're doing is, let's go back to my little diagram there. So we're just not going to get our vectors to match up that way. So if we increase that, we've also got to increase this vector, and we've got to increase that vector. So they've all got to be increased in tandem, in sync. Otherwise, so our k's and our omegas, or our k sine thetas and our omegas, all have to be working together. If they're not, then we're not going to then obviously this equality cannot be true. So that is why that has to be the true case, and that is why that has to be the case, which leads us to Snell's.